Hi everyone, and welcome to the Code Breakfast. I'm Markus, and I'm a PhD student focusing on machine learning with time series, and one of the core developers of sctime. And I'm really happy to be here today and to work through this tutorial with you. I'm joined by three other sctime contributors. That is Franz Kirai, who's a part-time lecturer at UCL and a senior data scientist in industry. And that's Patrick Rockenschaub, who's a PhD student at UCL as well, with a focus on epidemiology, and Ayushman Seth, who's a computer science undergraduate student at UCL. And they will be in the chat and happy to answer questions as we go along and help you out wherever necessary. We have 90 very exciting minutes ahead of us, I think. And so the main goal is to introduce you to machine learning with time series. And I think it would be nice if everyone could quickly write in the chat hi, so that we kind of like get to know each other a little bit better before we start. Okay, nice. Okay, so this is a beginner-friendly tutorial. We assume basic familiarity with the PyData stack, including pandas and scikit-learn, but not much more. So no previous experience of working with time series is expected. And it's also an interactive tutorial, and this is very important for us. So we encourage you to ask questions. Please use the chat. Please use the Q&A feature. We encourage you to run the notebooks locally or on Binder. So if you want to launch them on Binder, you can just go to the repo, which is up here, and then you can click the Launch Binder button, and you will launch it in the cloud. Otherwise, you can clone the repository up here, and you can then download the repository and launch the Jupyter Notebook locally. For more instruction, I've explained this here, how to get started. But yes, please use the code to play around with it, and we encourage you also to raise an issue on GitHub if anything doesn't look right or is buggy. So just to emphasize, this is a tutorial for you, and we're here to kind of like guide you through it and to help you. So the main learning objectives, actually, let me start the first notebook. Yes. So this is the introduction notebook. The 00 intro. And the main learning objectives are that you learn about the different machine learning problems and learning tasks that you may come across when working with time series data, and especially how you can tell them apart. You will also learn about different kind of specialized time series algorithms and different ways to build composite machine learning models to solve these problems. And the goal of the tutorial is not so much to propose new algorithms or to kind of like do comparisons of algorithms to find out which one is the best, but rather to highlight two things. And the first one is that there are many problems and pitfalls when you simply use kind of like scikit-learn to solve time series problems, which is not designed for these types of learning tasks. And second, that there are many interesting and effective other strategies of dealing with time series data that go beyond what scikit-learn and most of the other kind of like tabular toolboxes can offer. And throughout the tutorial, we will make use of sctime. And sctime is a new Python toolbox for machine learning with time series. And the idea of sctime is to extend scikit-learn to the time series setting. So we follow scikit-learn's logic and syntax wherever possible. So a lot of the code should look very familiar to you. But we also develop and implement new machine learning tools and techniques, especially for time series. There are also other a number of other time series toolkits out there, and here I mention a few of them. We have a more complete list of kind of like related packages and softwares in the Python ecosystem. When you follow this link in our main repository, again, feel free to chat to us or to raise an issue if anything is missing. sctime is a relatively young toolbox. We started a bit over a year ago, so some features are still experimental and will have to be consolidated in the future. So again, please make us aware if anything breaks or if you find any other shortcomings or bugs. In terms of the structure, we want to start by giving you an overview of the different time series data formats that you may encounter in real-world problems and the different learning tasks that you may need to solve when you have these data formats. And then we look at two learning problems in particular, forecasting and time series classification. And then for each one, we will show you how you can solve these tasks with standard approaches including scikit-learn algorithms, but also more specialized time series techniques and algorithms, which we provide in sctime. And then we conclude by giving you an outlook of how you can contribute to sctime and where we kind of like see sctime in the future. I think it also makes sense to have a 10-minute break in between. So perhaps after the first hour or so, that would be after the forecasting session or notebook, I think. Okay, so before we start, if you have any questions now, please feel free to ask them. Again, please don't hesitate to put them in the Q&A or chat. I think it's the first time for many of us to give an online tutorial, so it's even more important to kind of have like to get some feedback. And I'd really appreciate if you kind of like actively listen by giving me some reactions in the chat, kind of like indicating whether you can follow me, whether I go too quickly or too slowly, or whether anything is still unclear. Please also feel free to share related resources in the chat. And then any questions that we cannot answer in the Q&A or in the chat now, we will put on the Discord, and we're happy to discuss it afterwards. Okay, so I see there's one question in the Q&A. Yeah, so some of the questions I will try to answer live, and other questions the other contributors can just answer quickly in the chat. Okay, so is everyone ready to go with the notebooks? There's still an open question on. Yes, okay, so there are many questions now in terms of what's the kind of the difference of sctime and how it compares to existing toolboxes. Throughout the tutorial, we'll kind of like make references to other to kind of like a paper that we published on why we created sctime, and I guess also working through the tutorial will make clear what the purpose is of sctime and how it compares to other toolboxes. In short, sctime is a unified toolbox. So many of or all of the existing toolboxes, to our knowledge, focus on a few particular learning tasks. Like, for example, Profit focuses on forecasting. And some of the other toolkits I mentioned down here focus on time series classification only, or so on. And the idea with sctime is to create a unified toolbox for time series so that you can make use of kind of like relations between the different learning tasks and use algorithms for one task to solve another task. Okay, let's go to the first proper notebook, and let's make a start. So we'll start by doing some conceptual groundwork. And in this notebook, we're trying to give you an overview of the landscape of machine learning with time series. And I think this will really help us to clarify some concepts and to help us better understand what machine learning with time series is about and in what respects it's different from standard machine learning as presented in scikit-learn or in most textbooks. And this will hopefully also enable you to go off on your own after the tutorial and see where your own work is situated and help you in your search for more kind of useful resources. And in particular, you will learn about different data formats that arise in a temporal data context, different learning tasks that may arise in such a context, and how to tell them apart. And some of this may seem a bit obvious to you, but I think it's important to clarify these concepts before we kind of like start to do like write algorithms and try to solve learning tasks without having distinguished them clearly. Okay, so time series comes in many shapes and forms. And let's start with the kind of like simplest case here. So we only have a single series. And to make this a bit more tractable, we will consider an example. So let's suppose we are meant to analyze data from a chemical reactor. And I guess the goal could be to improve the outcome or the product of this kind of chemical process, or to like optimize the control system in like a smart way. And the chemical process takes place in this bioreactor. We have a little image here of the bioreactor. And the bioreactor is essentially a container in which chemical processes are carried out. And it allows you to control the process. For example, you can control the inflow of oxygen or the speed of the agitation system. But what we're mainly interested in is that the bioreactor also allows you to observe and measure certain variables throughout the process. And yeah, so in particular, it allows us to take certain measurements repeatedly over time using some sensor in the reactor. So this gives us time series data. And in the simplest case, we observe a single time series of measurements. And the time series that we observe consists of both the time points at which we make measurements and the kind of values that we measured. And let's say that we measure the pressure inside of the reactor over time. And here I've prepared some data. At the bottom of the notebook, you will find the reference to the data set. And I've just written a little helper function. So in this first line, we just load the helper, the data loading function, and then we can load the kind of the prepared data, and we can plot the single series. So this is a single time series of pressure. And now the question is, suppose that we only have this time series. What are some real world problems that you may encounter and that you may want to solve with machine learning? So two of the two most common ones are time series annotation, and kind of like special cases are outlier or anomaly detection and segmentation. And here you want to assign a label to each time point. For example, whether the measurement at a particular time point is an outlier or not, or perhaps you want to find change points in the process at which the kind of like the overall dynamics of the process fundamentally changed. So in time series annotation may be useful for if you want to develop like a live warning system, or as an analysis of where potential faults occur during the process that you observed. The other main learning task is forecasting. And here you want to make a temporal forward prediction using the available past data. And this may be useful to inform the control system of potential future changes to the process, so that you could have an early detection system that uses predicted data to make smart adjustments to the process. Okay, so much for the kind of like simplest case. How's everyone doing? Was that too slow, too fast? Are there any questions? I see there's one in the okay, this is still an old one. All right, thanks for all of the feedback. Looks like it's all going well. Okay. So the next complication is that you may observe multiple series, and here it gets a bit more complicated because this can happen in fundamentally two different ways. The first one is you can have multivariate time series where the time series are closely related, or you can have panel data where you observe independent instances of the time series. And we start with multivariate data. So here we observe two or more variables over time. For example, the pressure and now also the temperature of the process as well. And just to kind of like clarify some terms here, so variables represent different kinds of measurement, like for example, temperature or pressure. We take them within a single experimental unit. In this case, the experimental unit is the bioreactor run. So we observe a single bioreactor run and we take different kinds of measurements. So it's important to note that we still only observe a single bioreactor run, but now more than just one variable. And again, we can ask the question that if we have this type of data, what are some kind of like real world problems that we may have to solve and that we can actually answer with this type of data. So as before, we have like variants of the annotation and the forecasting tasks. But now we have access to additional variables, so we can make use of them. For example, now we can use not just the pressure, but the pressure and the temperature combined to see if the process at a particular time point was like an anomaly or an outlier, or just a normal observation. And similarly with forecasting, we can now use the additional variable as an exogenous variable and see if that can help us to make better predictions for the future of the process. Or we could try to forecast both series at the same time. So we forecast multiple series at the same time, and this is usually called vector forecasting. Okay, so the second way in which we could observe multiple series is panel data, or sometimes also called longitudinal data. And this is where things change a bit now, because here we observe multiple independent instances of the same kinds of measurements. For example, readings from the same sensor from different runs of the chemical process or the bioreactor. And I've plotted them here. So this is all different measurements of pressure over time, and each color represents a different run. And it's important to note that this kind of like difference between having multivariate data where time series are related and possibly dependent on each other, and having panel data where we can assume that the different runs are statistically independent. Also note that panel data may be multivariate, So we can have independent and identically distributed instances of multiple time series. So we could have observed pressure and temperature for multiple runs. And in this case, still the instances, the different bioreactor runs that we observe are independent, but the time series within each instance may still depend on each other. Also note that panel data may be mixed, so maybe we observe some time constant variables. For example, maybe we observe some fixed settings of the bioreactor, like the size, or some fixed control variables which cannot change over time. And again, we can ask the question, if we observe this type of data, what are some real-world problems that you may encounter and that you may want to solve with machine learning? So we have what we call supervised variants of the annotation and the forecasting task. And this now basically works as follows. So if you observe multiple runs and you have labels for the time points for the different series, you can try to learn the association between the process and the label from a training set, from the label data that you have. And then once you've learned this association, you can try to predict the labels of a new series that you get, of a new bioreactor run, which isn't labeled yet. So that's kind of the supervised time series annotation variant. Similarly, for forecasting, if you observe multiple bioreactor runs, you can try to make use of the consistent patterns across different bioreactor runs in order to predict the future values of a single series. But also with panel data, we can solve kind of like what we call series as features learning tasks. And these are direct extensions of the learning tasks that we have in scikit-learn. So we have time series classification, we have time series regression, and time series clustering. And what the goal is here is that we observe a time series, and in classification, we want to find the relationship between the series and an individual label. So we try to assign a label to an entire series. And in classification, this label is discrete, and in regression, we have the target variable, which is continuous. And then in clustering, we're interested in finding clusters of time series based on the similarity between entire series. And I've hinted at this before. We have to be aware of the kind of like statistical dependency structure of time series. And I guess the first point is quite obvious, but an intrinsic characteristic of time series is that observations are statistically dependent on adjacent or past observations. So, and this already indicates that they don't naturally fit into the standard machine learning setting, as in scikit-learn, where we assume to have independent and identically distributed instances. And yes, I've explained this before as well. So in multivariate data, it is implausible to assume that the different univariate time series, like the temperature and the pressure, that they are independent. But when we have panel data, it is plausible to assume that the different instances are independent, while the time series are still dependent on each other. Okay, so and at this point, having kind of like explained and outlined a little bit the landscape of time series, you may wonder, why does it all matter? Why do I have to care about this? And the main point here is that, well, there are two main points. So first of all is that different learning tasks require different types of algorithms to solve them. So for example, if you want to solve a time series classification task, you need an algorithm, or you need a time series classifier. If you want to solve a forecasting task, you need a forecaster. Now, more importantly, if you misdiagnose the learning tasks, if you think that you have to solve a different task than kind of the actual real world problem requires, your algorithm may still work when you build it in kind of like in your training environment, but it will no longer work when you want to deploy it, because it requires certain inputs that are simply not there in the deployment situation. And even if you misdiagnose the task, in many cases, you can still kind of get the algorithm to work and you can still obtain performance estimates. But these estimates are no longer reliable, basically, if you do not take into account the statistical dependence of the data. So performance estimates tell us how well our model will perform once we deploy it. And they basically allow us to make informed choices about which model to deploy. But our estimates are only reliable if we properly take into account the statistical dependence of the data that we use to obtain these estimates. Okay, let me check if there are many questions in there. No, okay. So is everyone still doing fine before we move on? I've seen there's like an active chat. I really appreciate this. Thanks for all of the questions and comments. Okay, nice. Okay, so let's move on. So there are a few more complications which we kind of brushed over here now. In many real-world applications, we find what we call time heterogeneous data. So the instances or variables may not share a common time index. And examples of this may be that you have unequal length time series data. So maybe the number of time points that you observe for the pressure variable are not the same as the number of time points that you observe for temperature. You may also observe timestamp data. So instead of observing measurements at a like regularly spaced interval, you observe measurements at exact time points. Or for example, maybe the different sensors have different sampling frequencies. And so the time indexes do not align. So maybe the pressure sensor samples the pressure from the process at like a 5-second frequency, and the temperature is sampled at a 3-second frequency. And in general, this kind of like having these different data formats raises the question how to represent this kind of data for the purpose of machine learning. And usually instances, what we describe here as instances, so the kind of like independent bioreactor runs, are represented in rows. Similarly, we have variables and or columns. Variables represented as columns, and then the time series setting introduces a new dimension to it, kind of the temporal dimension, the time points that we observe. And it's not immediately clear how to like best represent this. So there's like an ongoing debate about which format to choose. So whether we want to choose the wide format where we represent time points as columns, but that has certain drawbacks, or whether we want to choose the long format as in a relational database, or any other format. And similarly, there seems to be no consensus in the kind of like Python community about which data container to use, whether to use NumPy, Pandas, or Xarray, or even a custom data container. And for more details on this kind of like issue of how to store and represent this kind of data, you can look at our wiki entry, and there's also a notebook which we included, which Patrick wrote on the data container development and the kind of like thoughts and considerations that we took into account. And we're happy to answer more questions if that's of interest, either later or in the Discord afterwards. Yes, so regarding the question and the Q&A, yes, so that's basically the forecasting problem. So if you observe, for example, the last year, and you want to, and let's say you have like monthly data, and then you want to predict the next month of the new year, that will be a forecasting problem. We will explain the forecasting in more detail in our next notebook, where we focus like exclusively on forecasting. Okay, so to kind of like sum this up, we've discussed different types of learning tasks in briefly how to tell them apart. And for more details, you can take a look at our paper. And here we summarize the different learning tasks in kind of slightly more mathematical terms. And you can read through them or go back to them if anything is still unclear, or if you want to have like a slightly more like concrete and robust definition of them. Now, what's really interesting with time series is that there are so many of these tasks that are related. And until now, we focused on that these tasks are distinct, but there's this idea called reduction, which essentially says that an algorithm for one task, in some cases, can be adapted to help solve another task. And a classical example of reduction in supervised learning is one versus all classification, where you reduce a k-way multi-category classification. So you have k categories and you reduce it to k binary classification tasks. In the time series domain, there's also a very common example of reduction, and that's when you try to solve a forecasting task with kind of like regression algorithms from scikit-learn. And this is usually done as follows, which we try to kind of like show in the little diagram below here. So you observe a time series and you use a sliding window to split this into equal length windows, and then you stack on top of these, then you stack these windows on top of each other, and that gives you your feature matrix of lagged values. And for each window, you use the subsequent value as the kind of like target value that you want to predict. And so this is kind of what we call the like tabularization of the time series. And once you have this like tabular matrix, you can fit any scikit-learn regressor and then generate forecasts from it. We will just explain this again in the forecasting example in more detail. Here, the main purpose is to show that there are many relationships between time series learning tasks. And that's also one of the key reasons why it makes sense to have a unified toolbox, so that you can fully exploit these relationships. And here we kind of give you a quick overview of the different reduction relations that we know of in the time series domain. What I've just described, going from classical forecasting to tabular regression, in fact, involves a number of intermediate steps, but you can also, of course, kind of like directly reduce forecasting to tabular regression. Again, if you want to find out more or look up the kind of like references here in this little screenshot, you can go to our paper, which we've also referenced down here. And yes, this is the link to the data set. Okay. So this is kind of the conceptual groundwork that I think we needed for the more practical work. And yes, let me know if there are any questions at this point before we move on to the more practical forecasting task. Yes, so the link to the paper is right here, is right under the reduction diagram, if you can see it. If not, you will also find it on the SKTime repository. Okay, so let's move on to the kind of like first more practical notebook, which is the notebook 2 on forecasting. Okay, just to kind of like recap, in forecasting, we're interested in using past data to make temporal forward predictions. And scikit-learn provides kind of like algorithms and tools for building composite machine learning models to do that. And in this notebook, we'll kind of like look at both kind of like specific or statistical models to make forecasts, but also ways of building composite machine learning models, including techniques like reduction to regression, but also other techniques like ensembling and pipelining. And we'll kind of like work through them step by step. And then you can like play around with the code and ask questions, and we can discuss them in more detail. Okay, so we just load some preliminaries here. And then for this tutorial, we use like a toy data set just to clarify kind of the concepts. And this is an airline data set which shows the number of international airline passengers. And note that this is monthly data. So the seasonal periodicity is 12. And by the seasonal periodicity, we kind of mean the number of periods per year at which we expect to kind of like see like a seasonal pattern. And in this plot, you can see quite clearly that there's a strong seasonal pattern. Now, before we start building models to make forecasts, it is important to specify what exactly we're trying to predict. And this is something which is done very implicitly in scikit-learn. In scikit-learn, you know where have to like explicitly define the learning task that you're trying to solve. Instead, this is like implicitly done by your choice of estimator, so whether you choose a regressor or classifier, and also through the separation of the X and the Y, the features and the target in the interface or the signature of the fit function. In forecasting, you need an additional piece of information, namely the forecasting horizon. That is the time points that you want to predict. And here we define our learning task as follows. So we will try to predict the last 3 years of data using the previous years as training data. So each point in the series represents a month, as I've said. So we should hold out the last 36 points as test data. And then we use a 36 step ahead forecasting horizon to evaluate our forecasting performance. And to kind of like quantify the accuracy of our forecasts, we use SMARPy, which is the symmetric mean absolute percentage error. And to kind of like interpret this, a lower SMARPy means a higher accuracy. Now we can use this the temporal train test split function from scikit-learn from scikit-learn and define the test sites as 36, and then we can plot the data and we can kind of like see how we split the data into training and a test set. Opa. Let me load the data first. Okay. So we have 108 observations in the training set and 36 in the test set. Okay, as I've said, we now need to define the forecasting horizon, so the time points that we want to predict. And here we define it as kind of the range from the first step ahead to the 36th step ahead. We can simply define it as a numpy array. Yes, and we can then use this forecasting horizon to make kind of the predictions for the time points that we're interested in. Of course, you could also write it in a different way. So, for example, if you were interested in predicting only the second and the fifth step ahead, you could simply define the forecasting horizon as an array like this. Okay, I think it's usually a good idea to start with very like simple approaches to solve your learning tasks. that usually helps to clarify a little bit what we're trying to do. And for forecasting, two very simple strategies are, first, to always use the last value that we observed. So that basically means if I want to predict tomorrow, I just use the value of today. And the second strategy is if I want to predict, let's say, Tuesday, I look at the last Tuesday. So I use the last value of the same season. Now, if I want to do the predict the last value observed, so the first strategy, I could write this in Python in a single line. So we take the last value of the training set here, and we just repeat it for the length of the forecasting horizon. And then I cast it into a pandas series so that it has the right index, and that makes it easier to plot. So we can just plot this, and the green line that you see here, this is basically the prediction of the last value. Okay, we can also do this in skTime. And similar to skTime, we have, similar to scikit-learn, I mean, we have a naive forecaster or like a dummy forecaster. So we can easily specify it. And this syntax should be very familiar to anyone who knows scikit-learn. So we first build or specify the model, and we can choose the hyperparameters here. And we then, once we have specified the model, we can fit it. And here we use the single training series. And then once we have the fitted model, we now pass the forecasting horizon to predict, to generate these predictions. And then again, we can plot the data, and obviously it looks the same. And we can also compute the smart p-loss. Now, if we choose a different strategy, so to solve kind of to use the other strategy, the simple strategy, we can change the strategy hyperparameter and put in season or last, and at the same time provide the kind of like seasonal periodicity of the data, which is 12 in this case. And then you can see that this basically repeats the last season that we've observed into the future. And this already captures the kind of like seasonal pattern a lot better. So there's one question in the, okay, I think it has been answered already. Okay, so this should kind of clarify what we're trying to do. And now obviously we're interested in not just building naive forecasters, but kind of like more sophisticated models, which hopefully capture like underlying trends and patterns of the data in a better way. And now, of course, the question is, can I not just use scikit-learn? And the answer is yes, in principle, but there may be many pitfalls that you should be aware of and that you should try to avoid. So the first one, which is also maybe the most obvious one, is if you just use the train test split function from scikit-learn and you split your data, you basically get something like this. So train test split in scikit-learn is built for the setting where we have independent instances. So it makes sense to shuffle them and to randomly split them into training and a test set. Now, in time series data, you have a different statistical dependency structure. So you cannot just randomly shuffle the data because observations depend on past observations. And if we would use this kind of like randomly split data, we would run into a problem which is called leakage. So here, the data that you're using to train a machine learning algorithm happens to have the information that you're trying to predict. So basically, if we use this data to predict the last 36 steps, then as you can see, there's already a lot of training data there that the algorithm saw during training. So it makes it quite easy to predict this time period. But of course, you could use train test split from scikit-learn and set shuffle equal to false. And this is essentially what we do in the temporal train test split in skTime. And when you do this, it works. It splits it kind of like properly splits the time series and makes sure that you properly evaluate the performance of your algorithm. Okay, so the second pitfall is that it's not immediately clear how to use scikit-learn since we only have a single series. And this brings us back to the kind of like idea of reduction. So what we essentially trying to do when we use scikit-learn is to reduce the forecasting task that we're meant to solve to a regression task so that we can apply a scikit-learn regressor. And we can do this as follows. So again, we first need to transform the data into the required tabular format so that we can put it into the scikit-learn regressor. And as I've said before, we do this by using like a sliding window. We cut the series into windows, stack them on top of each other, and then always use the subsequent value as the target variable that we're trying to predict. And we could write some code for this. So for example, in the M4 competition, which is a famous kind of like forecasting competition, they have written some code, and I've used like a slightly modified version here. And this function basically does this kind of like transformation of the data for us. So it takes in a single series. It also needs the number of the kind of like the window length, which is the innum, and it needs the forecasting horizon, or the length of the forecasting horizon. Here, the number of out of sample points that we want to predict. Okay, if we run this function, now what I do first to kind of like illustrate a little bit how it works, I put in not the time series values, but I put in the time index basically of our time series. I set the window length to 10, and I give the length of the forecasting horizon. Now, if we run this, I need to define the forecasting horizon. Here we go. Now, if we run this, we can look at the kind of like feature matrix that we get in terms of the time index. And this looks as follows. So the first window is from the first observation to the 9th. So it's got length 10. Second one is from 1 to 10, and so on. So we kind of we can see this like sliding window. And then corresponding to these windows, we have the target variable, which for the first window consists of the next value. For the second window, it's the subsequent value, and so on. Now, this is when we use the time index. Now, if we actually supply the actual values that we observed, and then do the data transformation again, we can kind of see the shapes of the arrays. And so we have our feature matrix of lagged values has 98 rows, and as expected, kind of like a window length of 10. So we look at the 10 lagged values. And then we have the training target variable of the same length. Okay, and once we have this kind of like format, this is what scikit-learn needs. So we can just use any regressor from scikit-learn. In this case, I chose a random forest, and then we can just put it in and fit the model. Now, this all seems to work quite nicely, but we believe that there are like a few problems with this. And first of all, this requires a lot of handwritten code, which is often error-prone, and it's also not modular and not tunable. So by modular, I mean it's very hard to change certain components of this kind of like process. By tunable, I mean that this process, this type of reduction, involves a number of implicit hyperparameters, which we may want to optimize. So one of them is, for example, the window length. So the performance of the algorithm of the random forest and of this entire reduction approach is likely to depend on the window length that we choose. So we may want to optimize the value that we have by using like a temporal cross-validation scheme. Another hyperparameter is the strategy that we use to generate forecasts. Now we have the fitted model, but we haven't actually generated any forecasts so far. And how to do that is another kind of like modeling choice that we have to make as a like a practitioner or scientist. And we want to, in some cases, we may want to optimize this. And using this kind of like handwritten approach, all of this is like very difficult to implement. Now, before I show you how we can do this in skTime in a much better way, I want to kind of like show you how you can generate forecasts once you have this fitted model. So if we print the shapes of the test set and the feature matrix of the test set and the target variable of the test set, we can see that we have 36 windows, and each one is 10 long, so that seems to be in the right format. And we have kind of the target variable is the same. This is going to be kind of like our test set, so this is what we compare our predictions against. And now what we can do is we can simply put this in the fitted model and compute the loss. Okay, and now the question is, what's the problem here? So this seems to be kind of the most natural way of generating predictions. But given the learning task that we defined, it's actually wrong. And I think it's important to understand what's going on here. So when we put in these 36 windows, we use the actual test data rather than using kind of like predicted value or something like this. So in other words, instead of making multi-step ahead forecasts, so instead of having a fixed cutoff point and predicting 36 steps ahead, what we actually do here is we make 36 single step predictions. So we always move the cutoff. But that's a solution to a different learning task. And as you can see, we can still compute the loss, but this loss will be much more optimistic than the actual loss if we predicted 36 steps ahead. Because predicting only a single step ahead, having almost always the most recent data available, is likely to be simpler than predicting 36 steps ahead. So I think that's an important pitfall to kind of like be aware of. And now to fix this problem, we could write some code to do this recursively, as in the M4 competition. So what we do here is we define kind of like an empty list for the final predictions, and then we get the last window of the available data that we have. So in this case, it's the training set, and we use only the last window. And then we reshape it to make it into a 2D array so that we can use it in scikit-learn. And then we use only the last window that we have, and we generate a prediction. And then we kind of like do this recursively. So we iterate over the forecasting horizon. And for each step of the forecasting horizon, we first kind of like append or store our prediction, and then we update the window. And we update the window by using the last predicted value that we have. So we use the previously predicted value to update the new window. And then once we've updated the window, we can make a new prediction of the next step ahead. And we do this recursively until we've predicted all of the steps ahead. And then we can again compute the loss. And as you can see, so this loss, a smaller loss means a better accuracy. And you can see that if we do it this way, the loss is actually higher. So with this approach, we would have overestimated the performance of the algorithm. Okay, is this clear so far? Are there any questions? How's everyone doing? Okay, nice. So with skTime, we kind of like try to make this much more convenient for users. We encapsulate this reduction step into a meta algorithm. to make it modular and compatible with scikit-learn, but also tunable and adaptive in the sense that it adapts the scikit-learn estimator interface to that of a forecaster. And that makes sure that we can tune it and properly evaluate our model, and basically that we avoid the pitfalls described above. And this is kind of what we try to represent in this diagram. So we kind of like wrap the outer robot here is the reduction meta estimator, and it wraps the smaller robot inside the scikit-learn regressor. Okay, again, we can load the airline data, and we can do the temporal train test split, and then we can import from scikit-learn this reduced regression forecaster, which is essentially an auto-regressive regressor, so to say. So it uses the lag values as described above. And then we can, again, use any scikit-learn regressor. In this case, we now pick a k-nearest neighbors regressor. We specify the regressor, and then we pass the regressor to the reduced regression forecaster with certain hyperparameters. So here we use the window length of 12, which is the kind of like seasonal periodicity, and we use a recursive strategy to make predictions. And then this forecaster has the same interface as all of the other forecasters. We can fit with the training series and predict with the forecasting horizon, and then generate the predictions. And yeah, so this is what I've described before. This is kind of like how internally we split the window. I don't think I have to go over this again. So this is kind of the idea if we want to reduce the learning task to a tabular learning task. skTime has also other statistical forecasters like exponential smoothing or auto-ARIMA, which we interface from a nice package called PMD-ARIMA, which is linked here in the text. In the interest of time, I won't go through this in detail. I'll just skip over to the kind of like more interesting part that skTime has to offer. And this is kind of the composite model building functionality. One aspect of it is ensembling. And like scikit-learn, we have an ensemble forecaster where we can combine multiple individual forecasters and then average the predictions. And we're currently in the process of developing more kind of like sophisticated ensembling strategies to combine the forecasts of individual forecasters. This syntax, again, should be fairly familiar to anyone who knows scikit-learn. And just to kind of like reiterate, the ensemble forecaster wraps individual forecasters, but at the same time, it's a forecaster itself, so it has the same fit and predict interface as all of the other forecasters. Now that's ensembling. You can also do tuning in a forecasting setting, which is something that skTime provides. So we have the forecasting grid search CV, and we have different temporal cross validators. Here we use a sliding window splitter. And again, we define an initial window that we use for training the algorithm, and then we slide over the test set in order to evaluate it for tuning. And then once we have found a good algorithm through this grid search CV, we again evaluate it on the test set. So in this case, what we try to tune is the reduced regression forecaster, so this kind of like meta estimator, and specifically we try to find the best window length. Here I only look at kind of like 5 possible values, whether 5, 10, or 15 is the best choice. Of course, you could have a bigger grid of values to search over. And then once we run this, we will find that the best parameter is 15, and the kind of like the grid search CV will be we can then kind of use this with the best value to make predictions as in scikit-learn. Now another very interesting approach is residual boosting or detrending. And in skTime, we do this in a modular way. So here the idea is that you want to detrend the time series. And as we can see here, so the blue line is kind of the original training set, and there's a clear kind of like linear trend in the data. And what we can try to do is fit this linear trend and then subtract the trend from the data so that we only get the residuals. And this is what we do here. So we define a polynomial trend forecaster of degree 1. So this is just like a linear trend forecaster. And we have this detrender, which is a transformer, a time series transformer, which internally fits the forecaster, which we pass to it, and then returns the residuals of the time series. And this is basically what's happening here. So the YT is what we plot here, and this is kind of the residuals which we show here. Now, this is kind of like interesting to pre-process the time series, but you can, of course, also use this as kind of like a boosting strategy for forecasting. So you could fit any type of forecaster here and use the forecaster to detrend the series. So now we use like just a linear trend forecaster, but of course you could also use something much more complicated, like an ARIMA model or so, to detrend the series with the ARIMA model. And then on top of the residuals from the ARIMA model, so everything that the ARIMA model didn't capture, you can try to fit a more complicated machine learning algorithm. And this is kind of the idea of the detrender. And we show here how you can like combine it in a pipeline. So we have a transform target forecaster, which makes sure that you do target transformations in the correct way in SK time. So in here, the idea is that you first want to do some transformations of the data. For example, you want to take out the kind of like seasonal pattern of the data, and we use the kind of like standard seasonal decomposition technique here. And then once you've deseasonalized it, you want to get the kind of like a linear trend out of the data, which is what we do next. And then once you have the detrended series, you want to fit the more complicated model. In this case, we use the k-nearest neighbors again through this kind of like reduction approach. And we can all put this into a single pipeline. And again, then we have just the same interface, so we can fit and predict. And as you can see, this strategy already works fairly well. But again, this is not about showing which algorithms are best, but more to kind of like show you different concepts of how to solve a forecasting problem. If you're interested in kind of like algorithmic comparisons, we've used these different techniques and evaluated them on the M4 study, and you can find the link to the paper at the bottom. And of course, you can also look at the M forecasting competition itself. Okay, there's a question, prediction window still. So the prediction window is still kind of like, what we're trying to do is still kind of like encoded in the forecasting horizon. So the forecasting horizon here is still 36. So we still try to predict from the first step to the 36th step ahead. The window length 15 is what's kind of the look back. How many points in the past are we trying to use in order to make this prediction in this kind of like reduction approach? Okay, there are also other ways of kind of like, this changes the learning task basically now. If you want to make like more dynamic predictions, this is kind of like an online learning setting where you want to update your prediction as soon as you get new data. So, and we have a specific function for this, kind of the update predict function, where you can evaluate your model for different learning tasks like this one. So the dynamic forecast, just as the kind of like prediction intervals, which we show here, is still work in progress in SK-time and not kind of like comprehensively implemented for all forecasters. But yes, if you're interested, please get in touch. We're kind of like happy to push this further, and this is kind of part. And this is also on top of the kind of like development roadmap. Okay, so in summary, we've seen how to make forecasts. We've seen like different forecasting strategies, ensembling, detrending, and pipelining as kind of like novel techniques that go beyond scikit-learn, and which we provide in SK-time, in which seem to work relatively well in practice. I've added some links for more resources here. And this is the paper which I mentioned, where we try out these different approaches. This is a very good introductory textbooks on forecasting. And then more generally, take a look at the M4 competition and the currently running next iteration of that competition, the M5 competition. Okay, so I think it makes sense to have a quick break before we go into the classification notebook. We're already running a bit behind, I think, so maybe only a few minutes. I need to get some water, just a quick comfort break, and then I think we can meet back at 9:15 and 3 minutes before we, and then go into the classification notebook. I hope that's okay for everyone. Let me know in the chat how everyone is doing, or if you have any more specific questions. Okay, I'll be back in a minute. Yeah, so there's one question in the Q&A. Yes, that's correct. All of the steps in the pipeline must have an inverse transformation. You first transform the data, you then fit the forecaster and generate forecasts, and then you need to inverse the forecasted values to kind of like bring them back to the original scale. I hope that answers the question. So how's everyone else doing? Can everyone still follow? Any more? So someone raised a hand. I've seen this before. Please, instead of raising a hand, please put it into the chat or raise a question in the Q&A. Okay, there's still the question for how it compared to FB profit. I've mentioned this before. The main difference is that SK-time is a unified toolbox, so profit can only be used to solve forecasting problems. SK-time, as we will see in the next notebook, can also be used to solve other time series related learning problems. Yeah, I hope this answers the question. I also see that there are many kind of like practical questions about like in which situations would an ARIMA model be better than a machine learning model, and these are kind of like very hard to answer in general. I recommend the textbook, which I've linked at the bottom, and also to kind of look at the different benchmarking studies. Okay.
There's maybe one short point about Facebook profit. Mm-hmm. So to my knowledge, it just implements a very specific forecasting method. So it would compare to a framework toolbox to SK-time, like the random forest, Bryman's random forest compares to scikit-learn.
Yeah, I think that's right. It's a fairly flexible model though that they have.
Well, so is the random forest.
Yeah. Okay. If there are no more urgent questions at this point, let's move on to the next notebook, which is time series classification. So this is is kind of like now we're in the panel data setting, and I've tried to kind of like show what's going on in this diagram here, where we have training series which are labeled, and we have multiple instances of those. And then the goal is we get a new series and we want to label the new series. So we basically want to learn the association between the series and the labels. So we import a number of functions from scikit-learn and scikit-time, and then the specific data that we look at in this notebook is known as the arrowhead problem. So we're basically trying to classify the type of arrowhead based on the outline. And this kind of like shows that time series classification can be used to solve a wide variety of problems. So, and basically how you can go from shapes to time series is explained here. So let's look at, so here they try to kind of like transform the shape of a skull into a time series. And if we look at kind of like here, panel C, if we start at the mouth, this gives us our first time point. So the height here is the distance from the center point to the outline point, and then we move around it in like a clockwise fashion, and we always record the distance from the center point to the outline, and then we kind of get this. We transform the outline of the shape into a time series, and then we can try to see if the different outlines, if they help us to predict the type of skull, or in this case, the type of arrowhead. So in scikit-time, we kind of have this data set already, so we can easily load it. We have in our training set, we have 158 instances, and they're all univariate. So for all of them, we have a single time series. Now, this is where it gets maybe for some of you somewhat unintuitive. If we look at the data, this is basically what this like panel data frame looks like. So each cell has an entire time series in it. So if I take my X train and I look into my first cell, it has an entire time series in it. And the first number here is the index, the time index, and then we record the measurement value. So for the 0th index, we observe this value. For the first time index, we observe this value, and so on. So we represent entire time series as kind of like columns, rather than just having primitive values like floats, integers, or strings, as in kind of like the usual way of how you would use pandas or NumPy. And again, if you want to find out more why we make this choice, take a look at the wiki entry here, where we discuss this in more detail. If we look at our kind of like target variable, we see that we have 3 classes. They're not perfectly equally balanced, and we can plot kind of like here. I just plot like the first instance of each label to kind of see what the time series looks like of the different arrowheads. And again, we can ask the question, why not just use scikit-learn? And again, the answer is that yes, you can use scikit-learn, but again, you should be aware of certain kind of like implicit modeling choices that you make when you use scikit-learn to solve these issues. And there are basically 2 ways of how you could do this. So the first way is you treat each time point as a separate feature. So we can, this is again what we call tabularize here. So you can go from this format up here, where you have time series columns, to this format here, where each time point now represents a column. And this is kind of like a standard 2D matrix. So you can use this to fit your scikit-learn regressor. Now, the underlying modeling assumption here is that the orderedness in time of these observations doesn't play a role. So a tabular regression algorithm cannot make use of the fact that the columns are ordered. If you would reshuffle the columns, you would still get the same kind of like result, the same fitted model and the same predictions. But we can use this tabularized training data to, for example, fit like just to get like a baseline for comparison. We can fit a dummy classifier, or we could fit a random forest classifier. sctime provides also like a transformer for this operation, so you can make a pipeline where you first tabularize the data and then you fit the random forest classifier. And you can run this as like a encapsulated meta estimator. So this is what I've explained in terms of the implicit modeling choice here. And sometimes this works well. In some cases it may be suitable, but sometimes it doesn't work well. So here the kind of like what we want to kind of like show is that that there is an implicit modeling choice and that you should be aware of this, and that there may be other strategies which are more suited to the problem that you're trying to solve. The other way, so if we're back in this case, where we have series as features, the other way to go to the tabular setting is to use feature extraction. So we could, from each series that we have, we could extract certain features, and then this would also bring us back to the tabular setting of scikit-learn. And there's a nice toolbox for this called T is Fresh, and it does like automatic feature extraction for you. So here we kind of like show what this looks like. We use our kind of like panel data data frame, and we extract features from it, and then we can see that we have like different variables. So here, for example, we extracted the length. Here we extracted the maximum value. Here we extracted the mean, the median, and so on. And you can extract a number of features. This is kind of the minimal number of features. You can also use different settings to get many more features. And then once we have this data frame, again, you can fit a random forest classifier. So in sctime, you can formulate this as a pipeline with the feature extractor first and then the random forest. Okay, I want to show you one of the other kind of like more specialized time series classification algorithms which we provide in sctime, which shows like a number of interesting kind of like things that you can do with time series. And this is called time series forest, and it's a modification of the random forest algorithm. So the steps are, you first, so for each instance, you take the series and you split it into multiple random intervals. Then the second step is, for each interval, you extract a number of features. In the kind of like original implementation, you extract the mean, the standard deviation, and the slope. And then you basically, if you extracted 10 random intervals and you extract 3 features from each of them, you end up with 30 features for each instance. And then based on that matrix, you train a decision tree. And then you ensemble steps 1 to 3. So you ensemble this entire pipeline, including the data transformations and the final decision tree. So in sctime, we could write this as this in kind of like somewhat shorter form. But this one here explains it better, I think. So these are the steps of the pipeline. And in the first step, you choose a number of intervals. So here we use the square root of the length of the time series. And then for each interval, we extract the mean, the standard deviation, and the time series slope. And then based on these features, we fit a decision tree classifier from scikit-learn. And this gives us an individual kind of like time series tree. And we can use that as well. But we can also ensemble this, so we fit multiple of these multiple trees and then average their predictions. And this is what we do in the time series forest classifier. Another cool feature of this is that we can still get feature importances from this algorithm. And since we're working in the time series domain, we can get kind of a feature importance graph. So we can understand the feature importances over time. And this basically works by aggregating the importance of each feature from each interval, and then kind of like normalizing it by the number of intervals and estimators. And this may help us to better understand which parts of the time series and which features of the time series are important to discriminate between the two classes, or the three classes in this case. Another variant of this is called random interval spectral ensemble in the kind of like time series classification literature. And it works in the same way, but here we now extract different features. So we extract the autocorrelation, here the autocorrelation coefficients. We also extract the autoregressive coefficients and the coefficients of the power spectrum. But apart from that, the pipeline is the same, and then we can ensemble it again using this time series forest classifier, where we now pass the random interval spectral ensemble tree into it. Okay, another interesting approach to time series is k-nearest neighbors. And in scikit-learn, what you do when you do k-nearest neighbors classification is you look at the distance between individual data points. And you use something like the Euclidean distance. And you always do like a pairwise comparison. When you want to compare entire time series, of course, you could take the Euclidean distance between each time point and then average this. But this usually doesn't work particularly well. And the reason is that time series may be slightly shifted. As you can see in this image, that the bottom line is one time series and the top line is one time series. And they're just slightly shifted. And the Euclidean distance wouldn't be very small for these time series. But when you allow the kind of like matching between time points, when you give some kind of like slack to it and you allow this to be a bit more flexible so that you can find the nearest closest point when you compute the distance, you can kind of like define a similarity measure, which is much more suited to comparing time series. And this similarity measure is usually called dynamic time warping, or this idea of warping the series so that they align better with each other. And I've linked the Wikipedia entry, which is, I think, fairly well written, so you can read more details on there. And we have this implemented in skTime. So here we load a different data set, which is a basic motions data set. So we record the activities of students wearing like a smartwatch, and they do different activities. They play badminton, they run, they stand, and they walk. And the idea is, can we use this kind of like profile of movement to predict the class? And if you look at the kind of like, if we plot all of the instances for badminton, they look very messy, and they don't look as if they follow the same kind of like pattern, and the same for running. So if we would just use the Euclidean distance, it wouldn't work very well. But then if we allow them to be aligned through dynamic time warping, it works much better. And we can show this here. So this is the standard scikit-learn classifier with the Euclidean distance. And this is from skTime, the k-nearest neighbors time series classifier using the dynamic time warping. This is kind of like, you can find out other classifiers that we have and extra resources here. Now it's 9:30, and this is kind of the end of the talk. Before we finish, I want to quickly outline how you can get involved and how you can get started. So this is in the How to Contribute notebook. So you can check out the good first issues that we have. Please feel free to hang out in the Discord after the talk and get in touch. Feel free to raise an issue or to chat to us. It's all contributions are welcome, so not just code. So we have a lot of people who like write tutorials or who help us out by designing the toolbox and the interfaces. Yes, so SK Time is really a community-driven project, and where we would be very grateful if you would get involved and give us some feedback. All right, thank you very much.
Thank you. That was a really nice talk.
Thanks.
Good job. I think you managed to work it out well, even though virtual.
Yep.
Yeah, nice. So yeah, normally this is the moment you ask for like an applause, but that doesn't really work as well nowadays. Yeah. But yeah, thanks. I just been checking the Discord and the chat here, and people seem to have really enjoyed it. So.
Okay, nice.
Yeah, for follow-up, indeed, what you said, the Discord is available. We're also hosting sprints on Saturday, so actually if you got inspired by SK Time and want to contribute, maybe Saturday is also a good time to meet some like-minded people there and try to contribute a bit.
There's also an interesting talk at lunch today by Adrian Jalali.
Adrian Jalali, yes.
Scikit-learn.
Yeah. I was just about to say that the schedule for today is still very, very interesting. We have a sprint preparation session on writing unit tests, where Giovanni Lanzani will actually show a unit test that he written for Pandas in preparing this sprint prep session. Mm-hmm. After that, we'll interview Adrian. So Adrian is a core developer for scikit-learn. He's been involved with another project called FairLearn as of recently. We just want to pick his brain a bit on sort of the things that he's seeing there. And tonight we have three more talks on feature stores, on how it is to contribute to open source, and some lessons learned from managing an open data platform and using data for sort of civic good. So hope to see you all then, and hope to see you in Discord for now. Thanks.